Okay, hey all, welcome back. So this is another in our series of videos on Introductory Econometrics. In this video lecture, we're going to be talking about time series analysis. Now, before I get too far into this, please understand that time series analysis in econometrics is it's a complicated topic and generally receives its own class. So, for example, at the University of Wisconsin, Eau Claire, where I'm teaching, time series analysis is Econ 318. This course is Econ 316, Econometrics. So this lecture is really simply an introduction, or if you will, a launching off point to the material that would be presented in that course. So what are we going to talk about specifically here? We're going to talk about distributed lag models, which are a type of time series model. We'll talk about an application of a distributed lag model, is specifically Granger causality, which has many uses. We'll introduce the idea of dynamic models, which also have many uses in econometric analysis as well as in applied in say business analysis. We'll talk about some of the problems associated with dynamic models, specifically these types of serial correlation that we find in those models. And then finally, we'll talk about the topic of nonstationarity. Now, nonstationarity indeed also could get its own course. It's quite a complicated topic. But again, if you're sort of just interested, like, what is this? I hear people talking about nonstationarity of this, that. What does that mean? Okay, well, this is probably your video because that's what we're going to do. So hopping right into that, first, distributed lag models. What we're doing in distributed lag models, we're attempting to explain the current value of some variable. You pick it, right? Like, let's say unemployment, as a result of a series of variables, both in the current time period as well as perhaps historic time period. So we might say, like, the current value of unemployment is a function of a variety of things, like maybe the strength of the economy in the current time period, but then also of things in the recent past, like, for example, like quarterly sales 2 quarters ago or something like that. Okay, this is a distributed lag model. Now, a distributed lag model could employ variables in the current time period and historic periods, or it could be all in historic periods, right? The key idea is that we are incorporating data from the past to attempt to explain values in the current time period. Now, in these types of models, as well as all others that we have discussed and that we will discuss, we should understand that the estimated values of these betas, that is to say the marginal impacts of the relationships of these variables on the dependent variable, is always holding all other constant. Indeed, that's sort of the point of everything we're doing here, is to understand, say, okay, what is the impact of, to continue our unemployment example, what is the impact of the strength of the economy on unemployment, holding everything else equal. Okay, over here we see an example of a distributed lag model where we are attempting to explain the current value of a given variable based exclusively upon current values of some other variable, as well as lagged values of that variable. So in this case, they're all the same x, right? Effectively x1. It's not labeled that way because it's not needed because there's only one. So the value of x1 in the current time period, x1 in the previous time period, x1 in the previous time period, and so on. Okay, and so what we're trying to understand here is how a series of past events is impacting a present thing at the margin. So our dependent variable might be total sales, and then our lagged variable might be number of customers that came in the door today, and then yesterday, and the day before, and the day before, and the day before. Okay, and so explaining total sales as a series of one present value variable, and then a series of lagged values of that variable. And if the model is correctly specified, and we'll talk about the problems here in just a second with doing this type of analysis, but in this case, what we're shooting for is we're trying to understand the marginal impact of each one of those. So in my example, we may wish to ascertain, what what sort of days are our big days, right? Our big sales days, and what. Now, of course, since this is how we are estimating our betas, so we're looking at the variation, holding all our variation constant. You'd imagine, like, well, how could, wouldn't all those lagged values kind of be functions of each other? And the answer is probably yes. And this introduces the idea of multicollinearity, which is a problem in our work. Multicollinearity, you'll recall, occurs when two or more of our independent variables, our explanatory variables, are correlated in some way with each other. So like the classic example here is like income and wealth. We do have a whole separate video on this on multicollinearity, so you check that out if you need some more help on this. But when we have multicollinearity between two or more of our independent variables, which is almost certainly going to be the case in a distributed lag model, right? Because events in values in t-1 are almost certainly to be impacted by values in t-2, which are likely impacted by values in t-3, and so forth. In other words, there's going to be some kind of functional relationship between our lagged independent variables, introducing multicollinearity. And when we have multicollinearity, what happens is it becomes difficult to meet that holding everything else constant criterion. Okay? And as a consequence of that, what happens is that the sort of quality of our estimators declines. And what I mean by that is that the standard error and the variance, so the variance associated with our betas is going to increase, causing standard error, right, and causing our t-stat to be really less meaningful. In layman's terms, what that means is sort of the quality of our estimators declines. Okay, and the very straightforward reason why that is if you have multicollinearity, right, then there's some functional relationship between the two, and it becomes more difficult to assign specific variation in your dependent variable to this versus that independent variable. And so our explanatory power holding all of the things equal of any one of those variables declines. Okay, so let's consider an example of a distributed lag model. One of those is to determine so-called Granger causality. Now, what Granger causality is a specific type, a weak type of causality. What do I mean by that? Well, in economics, it's very rare, and indeed in most business analysis, it's very rare to be able to prove causality in sort of a physical way, right? So we think about causality in the most straightforward sense. If I have a lever, right, so if I take this cell phone, right, and I push down in this half, it causes the other half to go up. That is causal. It's mechanical causality. I push this end down, this end's coming up of a teeter-totter type of thing. Okay, it's rare that we get things like that in economics. But what we do get in economics a lot of the times is we observe movements of one variable leading another. So, for example, we might observe a stoplight turning red and then a bunch of cars stopping. Okay, this is an example of Granger causality. Stoplight turning red generally precedes car stopping. Okay, now is it the case that the stoplight turning red has caused the car to stop? Well, that depends upon what we mean by cause. In the literal mechanical sense, the answer is no. Okay, the car is caused to stop by the friction of the rubber of the tires upon the road. Okay, simply variations in one variable preceding another variable is not proof of causality. Okay, it is indicative, however. Okay, if we see one thing change a lot and it causes another thing to change, it's indicative of a sort of weak causality that we refer to as Granger causality. Okay, so if you hear that sort of fancy term, well, Granger causality, okay, that's what it is, right? It's a sort of weak form of causality. And what we're doing in econometrics when we're testing for Granger causality is we're testing to see whether a thing precedes another thing. So in this case over here, we're going to test to see whether A precedes Y. And we're going to do that using a distributed lag model. So in this case, we're going to run the equation yt, and we're going to regress that against lagged values of y, however many periods we feel is appropriate. In this case, we have 1 through p. And then we're going to add on to that our variable a through the same number of lagged periods. and estimate those coefficients. Then we're going to run an f-test on that equation to see if all the a's are jointly 0. And if they're not, right, we have evidence of Granger causality. Now, in order to really do this, right, now we need to run it the other way, right? Because we need to make sure we don't have some kind of weird chicken and egg type thing here. So we also, in order to get Granger causality, we're going to run it the other way as well. In other words, instead of having y on the left-hand side, now we're going to run a second regression with a on the left-hand side. Okay, then all of our lagged a's plus all of our lagged y's and associated, we're going to estimate the associated betas. Similar f-test there. Okay, should be the other way around. All right. Moving on then to the next type of models. This is dynamic models. Now in dynamic models, what we're doing is we're trying to understand how historic values of the dependent variable are impacting current values of the dependent variable. So for example, in the last time with the distributed lag model, you might be saying, okay, well, how past business revenues explain unemployment. Okay, here we might be saying, well, how past values of GDP explain current GDP. Okay, so it's a dynamic model. In this case, we see over here, okay, we have an example here of yt, so our dependent variable in the current time period, being a function of some variable xt, right, in the current time period, but also then the value of our dependent variable in the previous time period. Okay, now what about the previous time period? Okay, in other words, what's sort of the feedback loop, if you will, here? Well, we can similarly express yt minus 1 perhaps as something like this, where yt minus 1 is essentially a function, the same sort of function, but move everything back one more period in time. Okay, so in this case, our one independent variable xt minus 1 as well as our 2-period historic value of our dependent variable. So again, we might be saying this is like GDP, and then maybe like the xt is the global economy or something like that. Okay, the rest of the world. Okay, if we combine those ideas together, we're going to get something like the equation up on top. So this is just plugging in our hypothesized relationship for yt minus 1 into our yt equation. And of course, we can continue this for multiple time periods, getting something like this. Okay, so this is where we've now got the t minus 2, the t minus 3, so on and so forth. Okay, these types of estimated relationships are referred to as autoregressive equations. Okay, so if you hear that term, autoregressive model, that's what this is. So where you're explaining, you're sort of creating this backwards feedback loop in your model and saying, okay, well, the current is a function of a past, which is a function of the past, which is a function of the past, so on and so forth. Back for a variety of periods of time. Now, the autoregressive model cures some of the issues associated with the distributed lag model. So in a distributed lag model, if we were to run, say, several time periods, and we were to try to explain like several time periods against the current time period, it's unlikely that we would be able to fully isolate the marginal effects of each time period. Why? Multicollinearity. Okay. In other words, it's probable that history sort of causes like this. The further you go back in time, the less causality there is on the current time period. But with a simple distributed lag model, multicollinearity is going to cause the estimation of those lagged impacts to almost certainly not fit a nice curve, right? Whereas an autoregressive model will give us a clearer picture of the marginal impacts of those lagged time periods. Now that said, autoregressive models have their own problems, right? So every time you solve one problem, you end up with another one. That's just sort of the way of things, right? Dynamic models are going to suffer from autoregressive models are going to suffer from serial correlation. Now there's a whole other video just on serial correlation. So if you're needing a refresher on that, please see that video. All these videos are linked are included in a playlist, Introductory Econometrics, and they're titled accordingly. I think serial correlation is like the 9th one in this series, if I remember rightly, or something like that, somewhere in that range. Serial correlation, as you'll recall from that, occurs when observations of the error term are correlated with each other, right? So we have a series of residuals that follow some sort of functional pattern, and serial correlation, as you recall, causes OLS to no longer be a minimum variance estimator. In other words, it's no longer an efficient way of estimating. And it also introduces bias into our estimators. Okay, now like we reviewed before with serial correlation, we can test for that, and this is applicable to these dynamic models as well as it was in our more generic case in a previous video, using a Lagrange multiplier test. Okay, and the Lagrange multiplier test, I'm just going to cover it very quickly because we did cover it in depth in that video on serial correlation. Is this sort of two-step process. We're going to first obtain the residuals from the estimated regression equation, and then we're going to use those residuals as a dependent variable in an auxiliary equation. Okay, first here and here. Okay, and we're going to use the obtained statistic n, number of observations, times the r squared associated with the auxiliary regression as a test statistic and apply it to a chi-squared table. If the value of the test statistic is greater than the critical value from the chi-squared table, then we have serial correlation. And the correction for serial correlation is, as we've discussed, essentially you need to deflate the values, assuming you know how to, or assuming you know what the correct deflation factor is, as well as there's the possibility you can estimate the correct deflation factor to remove the serial correlation from your estimated relationship. Okay, now this introduces one of the other big problems with time series analysis, and this is the idea of stationarity, which we'll get into a little bit in just a second. But all that we're doing here is called regression analysis, right from the beginning. Okay, so regression. Why is it called that? First off, well, it's regression to the mean, right? So regression analysis is centered around the idea that things generally return to their mean values over large samples. And with time series analysis, so think about like GDP over time, or wages over time, or household incomes over time, or consumer spending over time. These things do not revert to their mean. They are non-mean reverting, okay? And as a consequence, a lot of our analysis is very much complicated. Okay, now what we have when we find these sort of time series relationships that are non-mean reverting, what we find is that it's very easy to get spurious correlation, right? Like, let's say we have two variables that generally increase over time. It could be like GDP and average American's weight or something like that. Okay, those that just go up, right? They're not causal, right? They don't. It's not one's causing the other. But we're going to estimate a beta between those two, right? We're going to be able to estimate a relationship, and the R squared is going to be really high, okay, between those two. But that's not. There's no explanatory stuff going on there. So anyway, stationary refers to you have these conditions, right? So the mean is consistent over time, the variance is consistent over time, and the correlation coefficient of x to its lagged value depends upon the lag, but not any other variable. Okay, if any of these doesn't hold in one of our variables or in the error term, we refer to that component of the estimated relationship as being non-stationary. Non-stationarity. So first off, before you get the idea like, well, it means you can't do it. No, it does not mean you can't do anything, but it means that the difficulty of forecasting values, of estimating relationships between different variables, has an additional layer of complication. Okay, now there are different types of non-stationarity, and of course, as you would guess, there are different types of corrections associated with different types of non-stationarity. We have trends, which is mostly what I've used in my examples, right? So this is where a variable or the error term is non-mean reverting, but it sort of follows a trend, sort of goes off in this direction, or maybe it even goes off in this direction, then it switches this direction, then it switches this direction, or okay, you get the idea, right? It sort of follows some type of pattern. Okay, so this is a trend non-stationarity, and so there's some examples here, right? But there are also examples of non-stationarity that are what we call a random walk, right? And so like Granger causality, non-stationarity, right? That's another one of those terms, right, that people love. Random walk means that a variable is non-mean reverting, but it doesn't follow a pattern, right? So it never, like, let's say it never comes back to a given value, right? But you can't use its current value to predict its t+1 value, and you can't, without knowing it, you can't understand its t-1 value from its t value. Okay, so it's some kind of random set of observations that don't revert to some mean. And so we can think of examples here is a lot of asset prices, like stock prices and things like that, are generally thought to follow random walks. You might think of like somebody who's had way too many beers, sort of trying to walk home. You don't. What are they following a pattern? Yeah, no, I don't know. They're just stumbling off kind of that way sometimes, and other times that way. Okay. All right. So enough of that. Like I said, this is an introduction to some of these topics. How do we test for non-stationarity? Well, now the first and the easiest way is to simply plot our values against their historic values, so in graphical analysis, right? We also can run an autocorrelation function. We'll do that in just a second, and the associated correlogram. And we can, the sort of bread and butter test is unit root test of stationarity. That is to use a Dickey-Fuller test statistic to determine stationarity, which we'll talk about these three in the remainder of this video. To determine how far correlation extends, right, we can use autocorrelation function as this. And then to determine the length of the leg, right, we can use to compute the length of the leg, right, we can use the autocorrelation function for, rough rule of thumb is between 1/4 and 1/3 of the entire time series, and then plot those estimated values against k, is the known sample correlogram. And that's going to look something like this. Okay, so this over here is from eViews, which is the software that we're using with this class. And so what we have here running down the vertical column is the autocorrelation AC associated with previous time periods. So t-1, t-2, t-2, 3, so on and so forth, right? And the degree to which that is correlated with the current t. So 9.7, 9.2, 8.4, 7.7, 6.9, okay, so on and so forth. Okay. Then finally, unit roots of stationarity, right? So here we're looking at the change in x, right? So delta x, okay, so change in x as a function of t, right? As well as t-1. Okay, so where the change in x is xt minus t-1, and we're testing to see whether beta 3 equals 0, right? So this is the unit root hypothesis. If beta 3 equals 0, okay, then the series is non-stationary, okay? But how to test this, right? So how can we construct a test to see whether beta 3 equals 0, right? What's the likelihood that beta 3 equals 0? the true beta 3 equals 0. Okay. We can't use a t-stat because this variable is non-stationary. We use what's called a Dickey-Fuller test or a tau test. And what we do is we use the critical Dickey-Fuller values to determine stationarity. If the computed tau or df value of the estimated beta exceeds the critical value, then we would say the series is stationary. Okay, then right at the end, you might have noticed it said correcting for non-stationary ... Right, correcting for non-stationarity gets quite complicated and really is beyond the scope of this course. I think we'll leave it there. That's probably enough, and we'll see you again next time. Take care, everybody. Bye.